6 feet below the surface of your yard. The ground temperature is 55 degrees Fahrenheit right now. It was 55 degrees yesterday. It will be 55 degrees in July when the surface air above it reaches 105. It has been 55 degrees at that depth every single day since before your house was built. And it will remain 55 degrees every single day long after the air conditioning unit on the side of your house has been replaced for the third time. That temperature is not an estimate. It is a measured geophysical constant confirmed by the United States Geological Survey, documented by the Department of Energy, and published in soil science data tables maintained by every agricultural extension office in the country. The earth below the frost line maintains a temperature equal to the annual average air temperature of your region, plus or minus 2 to 3 degrees, regardless of season, weather, or what is happening on the surface above it. This means that the largest, most powerful, most reliable cooling system on this planet is not a machine. It is the planet itself. And connecting your home to that cooling system requires nothing more than a buried pipe, a screened intake vent, and approximately $4 per linear foot of standard PVC. The technology is called an earth tube. Some engineers call it an earth-air heat exchanger. Others call it a ground-coupled cooling system. The ancient Persians, who invented it 3,000 years ago, called it survival. And despite being one of the most well-documented, well-tested, and well-understood passive cooling technologies in the history of building science, it is missing from virtually every modern home built in the last 80 years. This is the story of why. In the year 500 BC, the ancient city of Yazd sat in the center of the Iranian plateau, surrounded by one of the most hostile deserts on Earth. Summer temperatures exceeded 115 degrees Fahrenheit with regularity. Rainfall was virtually non-existent. And yet Yazd was not merely inhabited. It was a thriving center of commerce, scholarship, and architectural innovation that had persisted for thousands of years. The secret was beneath the city. Persian engineers had developed a system called the qanat, a gently sloping underground tunnel stretching from mountain water sources to the city below, sometimes running for miles beneath the desert surface. The qanat's primary purpose was water delivery, but the engineers discovered something far more valuable happening inside those tunnels. The air inside a qanat, surrounded on all sides by earth, at a constant temperature well below the scorching surface, was cool, dramatically cool. While the desert above baked at 115 degrees, the air flowing through the underground tunnel sat between 55 and 65 degrees Fahrenheit. A temperature difference of 50 to 60 degrees produced entirely by the thermal mass of the earth surrounding the tunnel. Persian architects connected these underground air channels to buildings through vertical towers called badgirs, wind catchers. These elegant structures, some rising 30 feet above the roofline, captured hot surface air and directed it downward through the building and into the underground passages below. The earth absorbed the heat from the air as it traveled through the tunnel. By the time the air rose through vents on the opposite side of the building, it had dropped 30 to 50 degrees. The result was a fully air-conditioned city in the middle of a desert, operating continuously, consuming zero energy, using zero mechanical parts, maintained by the constant temperature of the earth and the simple physics of convection. Some of these systems are still operational in Yazd today. 2,500 years of continuous service, cooling buildings the same way they cooled buildings when Persian kings walked those streets. The physics behind this are not complex, but they are remarkably powerful once you understand them. Heat moves in predictable ways. When warm air contacts a cooler surface, thermal energy transfers from the air to the surface. The air gets cooler, the surface gets slightly warmer. Given enough contact time and enough surface area, the air temperature will approach the surface temperature. An underground pipe provides both contact time and surface area. A 100-foot length of 4-inch PVC pipe buried 6 feet deep gives incoming air approximately 100 feet of continuous contact with a surface held at a constant 55 degrees by the surrounding earth. Air entering the pipe on a 95-degree summer afternoon loses heat to the pipe walls continuously as it travels through the buried section. By the time it exits the far end and enters the building, the air temperature has dropped to between 65 and 72 degrees depending on pipe length, diameter, airflow rate, and local soil conditions. That is a 23 to 30 degree temperature reduction, achieved through nothing more than the thermal mass of the ground and the time it takes air to travel through a buried tube. The Department of Energy published data on Earth tube performance, confirming temperature reductions of 15 to 25 degrees Fahrenheit in residential applications. Oak Ridge National Laboratory tested buried pipe heat exchange systems under controlled conditions and documented cooling output equivalent to 3 to 5 kilowatts of continuous capacity. That is comparable to a small central air conditioning unit running at full power. 3 to 5 kilowatts of cooling from a buried pipe, with no compressor, no refrigerant, no electricity, and no monthly utility bill, every hour of every sunny day. For the projected 50 to 100 year lifespan of PVC pipe in stable underground conditions. The Passive House Institute in Darmstadt, Germany, has certified earth tube cooling as a compliant technology for passive house certification, the most demanding energy efficiency building standard in the world. Buildings meeting this standard use 75 to 90% less energy than conventional construction. Earth tubes are one of the technologies that make those numbers possible. A peer-reviewed study published in the journal Renewable Energy measured earth tube outlet temperatures across multiple climate zones and confirmed that properly designed systems consistently deliver air within 5 to 8 degrees of the local ground temperature during peak summer conditions. The researchers concluded that earth tubes represent one of the most energy-efficient cooling technologies available for residential application in hot and temperate climates. The science is not new. It is not experimental. It is not controversial. It has been measured, published, peer-reviewed, and confirmed by every major building science institution that has studied it. And yet, the technology is virtually absent from modern residential construction. The question of why is where this story gets uncomfortable. The global air conditioning industry generates over $130 billion in annual revenue. This includes equipment manufacturing, installation services, maintenance contracts, refrigerant supply, and the single largest component of all, the electricity consumed to power the systems. The average American household with central air conditioning spends between $1,000 and $2,400 per year on cooling electricity alone. In southern states, this figure climbs to $2,000 to $3,600. Over a 30-year mortgage, a homeowner will spend $30,000 to $108,000 just on the electricity to cool their home. Add equipment purchase, replacement every 15 to 20 years, annual maintenance and emergency repairs, and the total lifetime cost of conventional air conditioning reaches $50,000 to $140,000 per household. An earth tube system for a residential home requires 100 to 200 feet of standard 4-inch PVC pipe at approximately $0.50 to $1.50 per foot. Add a small inline fan for assisted airflow at $30 to $50, a screened intake cap at $10, basic fittings and connections at $20 to $40. The total material cost for a complete system ranges from $120 to $500. Installation requires a trench 6 to 8 feet deep and 100 to 200 feet long. A rented walk-behind trencher costs $150 to $300 per day and completes the job in a single weekend. Total installed cost, including materials and equipment rental, sits between $270 and $800 for a complete residential system. The math is not subtle. $270 to $800 once versus $50,000 to $140,000 over a lifetime. For comparable cooling performance in the majority of climate zones where earth tubes are most effective. But the economic incentive structure of the building industry does not reward simplicity. It rewards complexity. Every component of a conventional HVAC system generates revenue for someone in the supply chain. The manufacturer sells the unit. The contractor sells the installation. The electrician sells the wiring. The maintenance company sells the annual service contract. The refrigerant supplier sells the chemical. The utility company sells the electricity. Every month, every year, for the life of the building. An earth tube generates revenue for the PVC pipe manufacturer and the equipment rental company. Once, and then never again. There is no service contract on a buried pipe. There is no annual maintenance visit. There is no refrigerant recharge. There is no filter replacement. There is no compressor that fails and requires a $500 emergency repair during the hottest week of July, when every HVAC technician in town is booked solid. The economic structure is not designed to suppress earth tubes through active conspiracy. It suppresses them through structural omission. HVAC contractors are trained on mechanical systems because that is what their industry sells and services. Building codes specify mechanical cooling requirements because code committees include representatives from equipment manufacturers. Architects specify conventional HVAC because that is what they were taught in programs funded by the industry that manufactures the equipment. Earth tubes are not prohibited. They are simply not included. They do not appear in the standard HVAC curriculum. They are not listed in the equipment specifications. They are not recognized by most code frameworks as a compliant primary cooling system. And in a regulatory environment where builders, inspectors, and contractors can only work with what the system recognizes, absence is effectively the same as prohibition. Now, before this conversation goes any further, the honest limitations need to be laid out clearly. Because understanding when earth tubes work brilliantly and when they do not is the difference between a successful installation and a disappointing one. Earth tubes work best in hot, dry climates. The American Southwest, the Mediterranean, the Middle East, Central Asia, arid regions of Australia and Africa. Any environment where daytime temperatures soar but ground temperatures remain in the low to mid-50s. In these climates, the temperature differential between surface air and ground temperature is enormous, and the air entering the tube is dry enough that condensation inside the pipe is minimal. In humid climates, earth tubes face a real engineering challenge. When warm, humid air enters a buried pipe and cools below its dew point temperature, moisture condenses on the inside of the pipe. This condensation must be managed through proper pipe slope and drainage to prevent standing water and biological growth inside the tube. In very humid regions like the Gulf Coast, earth tubes require careful design and may need supplemental dehumidification to maintain comfort. Earth tubes also do not cool as aggressively as a mechanical air conditioning system on the absolute hottest days. When outside temperatures exceed 105 degrees, an earth tube delivering 70-degree air provides significant relief, but may not achieve the 72-degree thermostat setting that a central AC system can maintain. In extreme heat, earth tubes work best as a pre-cooling system that reduces the load on a smaller, less expensive mechanical backup, rather than as a complete replacement. The system requires adequate property space for the buried pipe run. Urban lots with small yards may not accommodate the 100 to 200-foot trench needed for optimal performance, and properties with high water tables or solid rock at shallow depths may face installation challenges that increase cost and complexity. And earth tubes only produce cooling during the day when solar heating creates the temperature differential that drives the system. At night, the thermal draft diminishes. Nighttime cooling relies on natural ventilation through open windows, which works well in dry climates but less effectively in humid environments. But within the climate zones and property conditions where earth tubes are appropriate, and that includes the majority of the continental United States during the majority of the cooling season, the performance data is extraordinary. Here is what a properly designed earth tube system looks like in practice. The intake end of the pipe is positioned outdoors in a shaded area on the north or east side of the building. Shade prevents solar preheating of the incoming air before it enters the tube. A screened cap prevents insects, rodents, and debris from entering the system. The pipe runs underground at a depth of 6 to 8 feet, sloping gently at a 1 to 2% grade from the midpoint toward both ends to allow any internal condensation to drain out by gravity rather than pooling inside the tube. The length of the buried section determines the cooling capacity. Longer pipes provide more cooling because the air has more contact time with the cool earth. For residential applications, 100 to 200 feet of buried pipe provides effective cooling for a single-story home of 800 to 1,500 square feet. Larger homes benefit from multiple parallel tubes or larger diameter pipe. The pipe enters the building through the foundation wall or floor slab and terminates in a filtered vent that distributes the cooled air into the living space. A small inline duct fan, which can be powered by a 20-watt solar panel for complete grid independence, assists airflow on calm days when natural thermal draft alone may be insufficient. The system operates by temperature differential. Hot air rises. When the sun heats the south wall and roof of the building, indoor air temperature climbs. This heated air exits through high vents or open windows on the south side. As the warm air exits, it creates a slight negative pressure inside the building that draws cool air in through the earth tube on the north side. Cool air enters low. Warm air exits high. The building ventilates continuously with a stream of earth-cooled air that maintains interior temperatures 15 to 25 degrees below outside conditions without any electricity consumption. The installation process is straightforward enough for any homeowner with basic comfort operating a rented trencher or sufficient determination with a shovel. Start by checking your local ground temperature. Contact your county agricultural extension office or search the USDA soil temperature database for your region. If the ground temperature at 6 feet depth is between 50 and 62 degrees, your property is well suited for earth tube cooling. Plan a trench route from the north or east side of your property to the building foundation. The trench should be 6 to 8 feet deep and can follow a straight line, a gentle curve, or an L shape depending on your property layout. Avoid routing the pipe under driveways, large trees, or other permanent structures. Purchase 4-inch diameter solid wall PVC pipe, not perforated drain pipe. Solid wall pipe prevents soil moisture from seeping into the airstream. At $0.50 to $1.50 per foot, 150 feet of pipe costs $75 to $225. Add PVC elbows, couplings, cement, a screened intake cap, and a filtered outlet vent. Total materials sit between $120 and $350. Rent a walk-behind trencher for 1 day. Most equipment rental companies stock them at $150 to $300 per day. A trencher can cut a 6 to 8 foot deep trench through most soil types in a single day. Lay the pipe in the trench with proper slope for condensation drainage. Connect all joints with PVC cement. Install the screened intake cap on the outdoor end. Route the indoor end through the foundation into the space you want to cool. Backfill the trench and compact the soil firmly around the pipe. On the first hot day after installation, open a window on the south side of your home to allow warm air to escape. The earth tube intake on the north side will begin drawing cool air through the buried pipe and into your living space. Place your hand at the indoor outlet. You will feel air flowing at 65 to 72 degrees. The temperature difference is immediate and unmistakable. The air feels like it is flowing from a cave, because, in a sense, it is. The buried pipe is a manufactured cave that channels the constant cool temperature of the underground directly into your home. A homesteader in central New Mexico installed a 175-foot earth tube system during a single weekend last May. Total material cost was $290. He rented a trencher for $200. Outdoor temperature on the day he activated the system was 102 degrees. Air temperature at the tube outlet inside his living room measured 64 degrees, a 38-degree temperature drop. His home, a 1,100-square-foot stucco structure with moderate insulation, maintained interior temperatures between 72 and 78 degrees throughout the entire summer with the earth tube as his sole cooling system. His previous 3 summers, he had run a window AC unit that consumed approximately $340 per month in electricity from June through September. 4 months at $340 is $1,260 per summer. His earth tube cost $490 installed and has consumed 0 electricity in its first year of operation. The system paid for itself in the first 5 weeks of summer. Every week after that has been free cooling delivered from the constant temperature of the earth beneath his property. His neighbor, who was quoted $6,200 for a central air conditioning installation last spring, watched him dig the trench over a weekend and asked what he was doing. After seeing the results, the neighbor installed his own earth tube system the following month for $380 in materials and a day of rented trencher work. 2 homes on the same road, the same desert climate, the same brutal summer heat. Both maintained comfortable indoor temperatures throughout the season. One cost $490 and will never generate another bill. The other would have cost $6,200 up front, plus $400 per year in electricity indefinitely. The Persians figured this out 2,500 years ago in a desert that makes the American Southwest look mild. They cooled entire cities using nothing but underground tunnels and the constant temperature of the earth. Roman architects documented thermal draft ventilation principles 2,000 years before the modern HVAC industry existed. The Mughal Empire cooled palace complexes in 110-degree Indian summers through earth-coupled air channels 5 centuries ago. The Department of Energy published the performance data. Oak Ridge National Laboratory confirmed the measurements. The Passive House Institute certified it as a compliant cooling technology for the world's most demanding building efficiency standard. Peer-reviewed research in renewable energy and building and environment has validated the engineering across multiple climate zones. The physics has not changed since the Persians built their first comet. The Earth is still 55 degrees at 6 feet. The air still cools when it passes through a buried pipe. And the planet is still doing the work for free. It always has been. The only thing that changed is what we were told to buy instead. 55 degrees, 6 feet down. Right beneath the house you're sitting in right now, today, every summer, forever. A $4 pipe is all it takes to bring that cooling inside. The question is not whether it works. 3,000 years of engineering history and every peer-reviewed study ever conducted on the subject have answered that definitively. The question is why we stopped using it, and whether the answer to that question is one you're comfortable paying $140,000 to keep ignoring. If this story made you think differently about what cooling actually requires, consider subscribing. We look for the low-tech solutions that work, and the ones that have always worked. And we ask the question that matters most: why aren't we using them?